Hello everyone, this is Teacher Lou from Delta Learning Space. Today we are going to be chatting about the types of units we use in science, their prefixes, and conversions using dimensional analysis. Before we get started, I've linked a free SI units and conversions reference sheet and practice problems below. You don't need them right now. I'll provide all the conversion factors, but after the video, if you want to keep practicing, you can download those for free. Perfect. So let's start with what SI units are. The term SI comes from the French system International de Units, and it is the accepted unit system in many scientific disciplines. In the US, the standard system is called the Imperial system, and that uses units such as feet, miles, and gallons. But when we work in disciplines like chemistry, physics, and biology, we need to make sure that we record or convert our measurements to the SI system. Let's take a look at common SI units for a few different quantities that we can measure. The first is mass, which measures the amount of matter in an object. The SI unit for mass is called the kilogram, and its abbreviation is kg. The second is length, which measures the distance of an object or the distance between objects. The SI unit for length is the meter, abbreviated m. The third measurement we have for time is measured in seconds, abbreviated to s. Next, we have temperature. We commonly define temperature as how hot or cold something feels, but it can be more specifically defined as the average kinetic energy of particles in a system. The unit for temperature is the Kelvin, abbreviated to uppercase K. But in many settings, we also use degrees Celsius depending on the formula. The next measurement we have is electric current, which measures the rate of flow of a charge. The base unit is called the ampere, but we often hear it shortened to amp, but its abbreviation will be uppercase A. Our next measurement is one often used in chemistry, which measures the amount of a substance measured in the number of particles, and those can be atoms, molecules, ions, or electrons. The unit is the mole, abbreviated to MOL. Our second to last is the measurement of luminous intensity, which measures the visible light that is emitted and can be perceived by the human eye. This is measured in candelas, abbreviated to CD. And lastly, we have volume, which is not exactly an SI base unit, but it is a derived unit that we commonly use. Its SI unit is the cubic meter, abbreviated to m cubed. I included it because there are many times when we have to measure volume, like in gases. And just like with temperature, there is another unit for volume that we'll often see, and that is called liters. And that is abbreviated to uppercase L. You may be asking why we use these units in chemistry. And using SI units in our scientific disciplines is important because it keeps the measurements consistent and predictable. While the SI base units that we saw are standard, they are not always the most practical for every measurement. And so we use SI prefixes to help us adjust the units to a more convenient magnitude. For example, take our ant here. If we actually want to measure the length of an ant's body, a meter stick might not be the tool or unit that we use because it is much too large compared to our animal. But we can make adjustments using our prefixes and measure the ant in millimeters, which is much smaller and more appropriate for its size. Fun fact, black garden ants are roughly 3 to 5 millimeters long. In comparison, what if we want to measure the distance from the Earth to the Sun? A meter stick in this case would be much too small. We would need a prefix to help us show a much larger unit like kilometers. But even then, the average distance from the Earth to the Sun would still be about 150 million kilometers. SI prefixes are placed in front of the base unit and used to indicate magnitude. Our only base unit that we saw above that already included a prefix was the kilogram. And so in that instance, we would apply the prefixes to the unit gram. Let's take a look at some common SI prefixes that are used. The first prefix that we have is kilo with the symbol lowercase k, and that means 1,000, or in exponential form, 10 to the third. Let's apply this to the unit gram. What this means is that 10 to the third grams will equal 1 kilogram. So in our meaning in exponential column, it will mean how much of one base unit will be equal to the prefixed unit. Let's continue. Next we have hecto with the symbol lowercase h, meaning 100, with the exponential form 10 to the second. Then we have our next prefix, which is deca, with the symbol dA, meaning 10, or 10 to the first. Then we have our base unit, and this will be things like liters, grams, and meters. And so here, these will be the units without any prefix. And so this does not have a symbol, and it just means 1 or 10 to the 0. Next we have deci with the symbol lowercase d, meaning 0.1 or 10 to the negative first. And so that means that 0.1 grams will equal 1 decigram. Next we have centi with the lowercase c as our symbol, meaning 0.01 or 10 to the negative second. And finally, we have milli with the lowercase m as our symbol, meaning 0.001, and its exponential notation 10 to the negative third. So I want us to notice that as we go from kilo to milli, we get smaller by a base of 10 each time. And that's the nice part about the SI system, is that when we add prefixes, we are just changing by magnitudes of 10. But it is important to note that these are not the only prefixes. These are just the ones that we are showing here. In reality, more prefixes exist in either direction to express smaller or larger magnitudes. But one mnemonic device that we can use to help remember these prefixes is King Henry died drinking chocolate milk, to stand for kilo, hecto, deca, deci, centi, and milli. Because our SI prefixes are just changes within magnitudes of 10, one way that we can convert between the units with prefixes is using the ladder method. As you go down the ladder, or going from kilo all the way down to milli, you move the decimal place of your given number to the right as many places as you go down the stairs. So as you go down the ladder, we move our decimal place to the right. And as you go up the ladder, you move the decimal places of your given number to the left as many places as you go up the stairs. Let's take a look at what that means in practice. In our first example problem, we are given ml and are looking for the equivalent measurement in liters. So we are going from milli to our base units. So we would start at our lowercase m, and that means we have to go up the ladder 1, 2, 3. And so we are going to take our 1, which always has a decimal to the right of it, even if it's not shown, and we are going to go to the left 1, 2, 3, and fill in placeholder zeros. So 1 milliliter will equal 0.001 liter. Our next problem gives us 30 kg, and we want the equivalent measurement in mg. So now we are starting at the k and going all the way down to our m, which means we are going down the stairs 1, 2, 3, 4, 5, 6 steps. And we will have to move our decimal place 6 steps to the right. 1, 2, 3, 4, 5, 6, and fill in our placeholder zeros. So 30 kg is going to be equivalent to 30 million mg. Now we have our last problem. Pause the video and try to answer the question on your own. In this one, we are going from cm to dm, which means we are going up the ladder once. And so 5.7 centimeters will be equal to 0.57 decimeters. The latter method works great for metric to metric conversions, but it won't work for every situation, especially those across different systems. But luckily we have other methods that we can use for those conversions. And so we are going to take a look at the dimensional analysis method. 1. Write the given value in unit. 2. Multiply by a conversion factor written as a fraction. 3. Place the unit you want to eliminate in the denominator, and this one's going to be key. 4. Check that the unwanted units cancel. And 5. Perform the math and write the final unit. If your units cancel correctly, then your setup is correct. If your units don't cancel, don't do the math just yet. Fix your setup first. Let's take a look at dimensional analysis in action by taking another look at converting 30 kilograms to milligrams. To complete this problem, we are going to use the following pathway. We are going to go from kg to g and g to mg. And pathways can be helpful when doing multiple conversions or when just solving different problems. We also know the following conversion factors. 1,000 grams will equal 1 kilogram, and 0.001 gram will equal 1 milligram. This is only one way that these conversion factors can be written. There are multiple ways. For example, it could have been 1,000 milligrams equals 1 gram, but I am basing it based off our table. And so now we can follow our steps. The first thing I want to do is I want to put my given value and unit. So I have 30 kg, and I like to set it up as a fraction. Then I'm going to put a multiplication sign and set up another fraction and write my first conversion factor. I want my kg to cancel, so that means I'm going to put my 1 kg down below with my 1,000 grams above. And so that means my kgs will cancel out, leaving me with my unit grams. If I do this math, this will give me 30,000 grams. And now this will be my new given as I go from grams to milligrams. I have 30,000 grams and I'm going to put that over 1, set up my multiplication, and write my second conversion factor as a fraction. But I want to cancel out grams, so that is going to go in our denominator, 0.001 gram. And my 1 milligram will go on top. And I am going to do this math, which essentially comes down to 30,000 divided by 0.001. And that's going to give me 30 million with my grams canceled out, leaving me with my desired unit of milligrams. This conversion can also be done in one long pathway, like this. And so all I did is condense the steps to follow the pathway, because we are going from kilogram to gram, but then our grams are canceling out, leaving us with our final desired unit of milligram. Pause the video now and try practicing dimensional analysis on your own. Before you get started, think about the pathway you have to follow and what conversion factors that you will need. And so here's our pathway with our conversion factors. I'm using my first conversion factor, that 0.01 meter equals 1 centimeter. And here I have my dimensional analysis set up. My centimeters will cancel out, leaving me with meters, but then my meters will cancel out, leaving me with hectometers. I can now put that into the calculator, and my final answer will be that 8 times 10 to the 4th centimeters will be equal to 8 hectometers. The nice part about dimensional analysis is that it can be used in many different instances, and we can use this method to not only convert SI units, but to convert imperial to SI units as well. All we need before we get started is the conversion factor. In our problem 6, our conversion factor will be that 1 kilogram will be equal to 2.2046 pounds. So we will start with our given of 400.5 pounds, put it over 1, set up our multiplication with our fraction, and our next step is going to write our conversion factor, but we do want to cancel out pounds, which means that 2.2046 pounds will go in the denominator, and our 1 kilogram will go in the numerator. And in this calculation, this essentially comes down to doing 400.5 divided by 2.2046. And when we do this calculation, we get 181.66 kilograms, but rounded to 4 sig figs, this will round to 181.7 kilograms with 4 significant figures. Pause the video and use dimensional analysis to find out how much 400.5 kilograms is in pounds. And so here we'll use the same conversion factor with 400.5 kilograms over 1. But we do want to cancel out kilograms, and so 1 kg will go in the denominator with 2.2046 pounds going in the numerator. And so here we have our kgs canceling out, leaving us with pounds. And when we do this math, we end up with 882.9423 pounds. And when rounded to still 4 significant figures, because here we have our limiting significant figures, that ends up being 882.9 kg. Now that we've had some practice with dimensional analysis, let's take a look at when we are not dealing with linear units, meaning we have units to the 2nd or even 3rd power. And this can happen when we are converting areas or volume. Our first problem, we are converting 1 meter squared to centimeter squared, and we are going to use the conversion factor, that 0.01 meter equals 1 centimeter. So I want to take a look at what that actually means when we have something squared, and that is going to be something very similar to area, where we have one dimension going one way and another dimension going another way. And so when we do this conversion, we need to make sure that we do it twice to represent that the change is happening both in 1 and 2 dimensions. But we'll set up our dimensional analysis problem more or less the same. We end up at 1 meter squared over 1. I want to go from meter squared to centimeter squared, so that means this will be on bottom. So that way we'll cancel out. But as we see, this doesn't purely cancel out. If I cross this out, I'm still left with a meter. And so to fully cancel out meter squared and give us centimeter squared, I have to do this twice. Because not only will my 2 meters from the numerator cancel out with my 2 meters from the denominator, but now I also have 2 centimeters to give me centimeters squared. And so now I put this into the calculator, making 1 meter squared equal to 10,000 centimeters squared. Now pause the video and try to convert our final example. And so here we have our dimensional analysis set up. We have centimeters cubed, which means to fully cancel out, this has to happen 1, 2, 3 times. And to get meters cubed, 1, 2, 3. Doing this calculation ends up getting that 1 centimeter cubed will be equivalent to 1 times 10 to the negative 6 meters cubed. And all dimensional analysis is canceling out the units that we're given to get the units that we want. Thank you for sticking it out all the way to the end, and I hope that you have found this video helpful. For more units and conversion resources, check out our blog or download the free reference sheet or practice problems. Keep learning, you got this.